So continuation of chapter 13 notes. What I'm going to talk about in this one is Raoult's law according to volatile solutions and how that plays or is different from non-volatiles. So volatile means the solute that you're putting in there goes to vapor. So draw a beaker over on the side. You have a mixture of A plus B in the vapor as well. Okay, so in the previous example of the non-volatile, all I had was the solvent in the vapor form. So because both of them are going to go to vapor, you're essentially going to do kind of like Dalton's law, where you're going to add the two pressures together. So the pressure of A, whether that's the solute or the solvent, and the pressure of B times the mole fraction of each. So I'm going to explain this two different ways. One, according to ideal solutions, and then a second way according to non-ideal. So ideal, we're going to use benzene and toluene as our examples here. And I'm going to write down their vapor pressures. Benzene is 95.1 torrs, and toluene is about 28.4 torrs. So just by looking at their vapor pressure, benzene is more volatile than toluene because it's at 95.2 torrs. That means more of it above that liquid is going to populate than the toluene. So the graphs that you see here on this page, I still can't find a better graph than this. So I need you to kind of look at a couple things and ignore other things. So on the x-axis is the fraction of benzene. So if you want to draw a little benzene down here so you could recognize it. And what we are doing is going from 0 to 1. So what that means is this point up here is all benzene, okay? So if that's the case, it should be at 95 torrs. The only thing I don't like about this graph is the fact that those numbers don't match up. So if I only have benzene in there, I'm going to have a total pressure of torrs 95.1. Over here at 0 would mean this is all toluene. And that pressure is at 28.4. Okay, so this line itself, okay, that I'm highlighting right now, this line itself is essentially what we call the vapor pressure of the mixture. So depending upon how much benzene and how much toluene you have a different vapor pressure above that mixture. So again, think of the A plus B above that mixture. So this line, this straight line, you could predict off of, depending upon how much you have. So what you do is you essentially take the pressure of the benzene is going to be due to how much benzene you have in there, the mole fraction, times the overall pressure, which is the 95.1. The toluene, how much toluene you have, and then you add them together, okay? Also note, in terms of calculations, your overall mole fraction will always equal 1. So if you have one of them, you could find the other one in terms of calculations. Okay, so next page is what we call non-ideal. Non-ideal. So in the case of non-ideal, you have two different discussions. One is what we call a positive deviation, okay, from where the ideal behaves. And then the second is what we call a negative deviation, okay. So I am going to look at positive deviation, explain it that way. So over here, draw a beaker. I have a mixture of A and B, and I have a lot of A and B above that liquid. This is when the forces are weak in both A and B, okay? So that would mean I have just dispersion forces in both the solute and the solvent, okay? So the ideal is this straight line, okay? So do realize there's a lot of lines here that I don't want you to focus on. Instead, I want you to focus just on this curvature up, okay? This curvature up. So the orange, okay, is the ideal. So that's how the ideal behaves. A positive deviation means you get a greater pressure above that liquid than you predict mathematically. So mathematically, you're going to add up A plus B, just like you did with the ideal, but instead you're going to say that that number that you produce in the calculator is a much higher value. So let's say, for example, I had like an ether, okay, which would be, again, an oxygen between two carbons. And let's say I have some kind of alkane, okay, where it's just single bonded molecule, okay, and I mix them together. Well, I would find the total pressure, so again, it'd be due to A plus the pressure of B. So let's say they added up to 52.1 torrs, and I'm just making up numbers just to have a discussion. So the total pressure you would predict is greater than 52.1 torrs. So if you had the pressure of ether, you had the pressure of the alkane, and you added them up when you multiplied them by the mole fraction, and you get a 52.1, what you would say is the actual pressure above that liquid is greater than. Okay, so that's why it slopes up, and we have that curvature there. Okay, so there is more vapor, write down more vapor than predicted. Okay, because it has what we call a positive deviation, So then we have what we call negative deviation with a non-ideal solution. So again, I have A plus B in the beaker, and I have A and B above the liquid. So I do have vapor. But realize I have less A and B in this case. So what I have highlighted in orange there is the ideal situation, okay? And then in pink is what I call the negative. So it's going to go lower than predicted. So this is when the forces are strong in A and B, okay? So let's say I'm mixing water with alcohol. Alcohol has an OH group. So both of them have what we call hydrogen bonding, okay? So hydrogen bonding is the strongest force when we're talking about intermolecular forces. And so when I'm looking at the pressure, I could say, again, the pressure is due to the water and the alcohol. Both of them are volatile. Both of them will populate above the liquid. So let's say when I add them together, they're around 63.8 torrs. Again, I'm making up numbers here. I would then say for my final answer that my total pressure is less than 63.8 torrs because I would have less vapor than predicted. So if the forces are strong, you're going to say it has a negative deviation. If the forces are weak, you're going to say that it has a positive deviation. And again, it is due to the fact that you are talking about how much is volatile and how much is not in terms of the solution. So now I'm going to kind of go through an example calculation with you. And the calculations are the same for ideal and non-ideal. The only difference is I'm going to tell you if it's non-ideal. And so then you would say it's a higher or lower number depending upon the forces. So you'll have to know what the molecules are. But the math is exactly the same. So what are the partial and total vapor pressures at 25 degrees Celsius above a solution with equal numbers of molecules of benzene and toluene? So back to the other page, the vapor pressure at 25 degrees Celsius of benzene is 95.1, toluene is about 28.4 torrs. And so if you have equal molecules of benzene and toluene, that would mean their mole fraction is 0.5 for each one of those. So then to find the partial pressures, all you have to do is take the 0.5 times the pressure at 25 degrees Celsius. And for benzene, it's 47.6. When you do the toluene, it comes out to be 14.2. So when you add them together, the total vapor above that liquid is about 61.8. And again, if my graph was beautiful, and it is not, you would go to 0.5, you would read that, and that would be approximately 61.8 torrs on the graph, okay? That's where that number is coming from, okay? So that's exactly the same calculation over and over again. So then I would say this is part B. What is the percent composition of the vapor in the equilibrium with the benzene toluene solution above? So this is talking about the vapor itself. How much of it is benzene, how much of it is toluene, okay? Now you could infer, because benzene is more torrs than the toluene, that you would have a higher percentage for benzene than toluene. You should prove that. So again, benzene, you take the individual partial pressure over the total, times it by 100, so 77% of it is benzene. And then toluene, subtract that from 100, or you could do the math over here, is 23. In general, okay, in an ideal solution for two components, the vapor is always going to be richer, meaning you have more of it, okay, with the more volatile compound, okay, because again, volatile means it goes to vapor easily. So that means benzene is more volatile, so you're going to have more of it above the vapor.